Welcome back, everyone. This is Professor Herring. In this video, we're going to do a couple more practice problems dealing with Chapter 15, looking at reaction chemistry and redox reactions in particular. Let's begin. So, read over the question and pause the video and try this on your own before proceeding. Welcome back. So to write the net ionic equation for the reaction, what we first need to do is determine the molecular equation. And that's going to be sodium phosphate reacting with silver nitrate. When you look at the solubility rules here, sodium and nitrate compounds are always soluble, which means then that these are going to be listed as aqueous. And then we need to swap. So the sodium now is going to interact with the nitrate and the silver with the phosphate. And you need to pay attention to the charges here. Let's draw up above this line the charges on each of those elements. Sodium is +1, phosphate's -3, silver is +1, nitrate's -1. Now how do you know about the silver? That you can figure out via deduction by knowing that the nitrate's -1. So we have then +1, -1. Well, then those are good. We have a +1 and a -3, which means we need to put a 3 as a subscript here. Remember that your polyatomic ions stay together, so the nitrate and the phosphate stay together. Now, when we look at the states, are these going to be aqueous or solid? Again, sodium and nitrates are always soluble, so that's going to be aqueous. And then silver and phosphate. Well, so we find phosphate down here. We see that it's insoluble unless when bound to ammonium or one of the group 1A metals. Since that's not the case, this is going to be solid. It's going to form a precipitate. Then, when we do the full ionic equation, we dissociate into the component ions. Keeping in mind that if it's a monoatomic ion, any subscripts go and modify as coefficients. Polyatomic ions, again, will stay together. Ooh, before we go on here, guess what? We didn't double check to make sure it was balanced. So let's do that. We've got 3 sodiums here and only 1 here. Now we have 3 nitrates here and only 1 here. Now we have 3 silver, 1 phosphate, and 1 phosphate. Okay, we're good to go. So now we need to make sure that we account for that in our full ionic equation. And again, when we form anything that is a solid, liquid, or gas, it stays together in the full ionic equation. Now we look for anything that is the same on both sides. We have 3 sodium and 3 sodium ions, 3 nitrates and 3 nitrates, and then everything else stays. That means our net ionic equation is going to be phosphate ion plus 3 silver ions reacting to form silver phosphate precipitate. Okay, and that's it. If we ask what's the driving force, that'd be the formation of the precipitate. All right, let's move on to the next one. Balance each reaction, classify, and determine the driving force for each. All right, so pause the video and you try this on your own first. Welcome back. So when balancing, what you want to do is you want to pick a given element that only shows up in one side of the in one molecule or one place on each side of the reaction. So for this first one, it doesn't actually matter which one you start with because sodium only shows up once in the reactants and once in the products. sulfur is the same. And since that's the case, I'm just going to arbitrarily pick sodium. So we have 2 sodium on the left. We have one on the right, so now we have 2. Okay? Let's take a look at sulfur. Sulfur, we have 1 on the left, 1 on the right, so we're good so far. Hydrogen, we have 1 on the left and 2 on the right. So let's put a 2 here. And now we have 2 and 2 chlorines. Okay, so we're balanced. What type of reaction is this? This is a double displacement. We can see that we have A, B, and C, D. And now A is with D, and B, or rather I guess this is C, C is with B. So that's a double displacement. And then the driving force is right here. It's the formation of a gas. Second one. Now in this case it matters which one we choose. If we start by balancing oxygen, we're going to be in big trouble. So let's ignore it until the end. Let's instead pick one of the other elements. Start with carbon. 4 carbons on the left, 4 carbons on the right now. Hydrogen, we have 8 on the left. Now we have 8 on the right. Oxygen, we have 1, 2, 3, 4 so far. And then we've got 8 here and 4 here for a total of 12. So we need to modify then this one here. If we change the coefficient here, that's going to change everything we've already done. So instead, we need to figure out how many oxygens we need here. We have 4. We need 8 more. And so we need to add essentially a value. This value is already 1. We need to add 4 more here to get a value of 5. And that's going to be then now 2 plus 10 is 12. This is a combustion type reaction. And the driving force, you can say that it's the formation of a gas because we're forming more gas in the product than in the than we started with. Really, this is actually a type of a redox reaction. All combustion reactions are redox reactions. Okay, number 3. So start by balancing it. We have so far we've got 2 nitrogens on each side, so that's good. Hydrogen, we have 4 on the left, so let's put a 2 here. And now oxygen. We've got 3 oxygen on the left and 4 on the right. So how are we going to do this? This is where you can see that in some cases you're going to have to go through what's called an iterative process, where you maybe go back and forth. And so we're going to have to increase the number of oxygens on the left, or really one way that we could do this is by making this be 1/2. If we do that, now we have 3 on the left and 3 on the right. It's actually balanced. But usually we like to have whole numbers. So if we multiply everything by 2, then we get the coefficients of 2, 2, 1, and 4. And now it's still balanced, but we have our whole numbers. We change then just to double check. We have 1, 2, 3, 4 nitrogens on the left, 4 on the right, 8 hydrogens on the left, 8 on the right, and 6 oxygens on the left, and 1, 2, 3, 4, 5, 6 oxygens on the right. Great. This is a decomposition type reaction. And the driving force. Here we have formation of a gas, definitely. But it turns out that this is also a type of a redox reaction. If you were to look at the oxidation states, you would see that our nitrogen is being affected, as is the oxygen. Here, its oxidation state is 0 and 0, whereas here it was -2. And here, let's see here. We would have 4, 6, 1 plus 1 each. Okay, this last one. So it doesn't matter which one we start with. Let's just start with nitrogen. We have 2 on the left. So we need to put a 2 here. And now we have 6 oxygens on the right, or excuse me, 6 hydrogens, and we need to put a 3 here. So we have 6 there. This is an example of a combination type reaction. And you might be tempted to say that the driving force is the formation of a gas, but it is not gas formation. And the reason for that is because we have only 2 gas particles formed, but we used 4. So we're not actually forming gas. Instead, this is another redox reaction. Alrighty, let's go on to our last problem. Determine the oxidation state of each bolded element for each substance. So, one of the rules you need to remember is that the sum of all oxidation states has to add up to this charge on the ion or species. And I'm going to leave it at that because you should pause the video now and try this first. All right, welcome back now. So resuming, the sum of the oxidation states has to add up to the charge on the species. So we know that we have to add up to -1, 0, 0, and 1. Okay. Now let's go through one at a time. We deal, generally speaking, with the group 1A, 2A, and then fluorine, and then the most electronegative elements. Fluorine and hydrogen, and the most electronegative elements. Some other things to consider are whether or not we have, remember that if we have an ion, we have to account for that, or if it's purely elemental, then its oxidation state is 0. But when we're dealing with compounds, our approach should generally be evaluate for group 1A and group 2A, then fluorine, then hydrogen, and then the most electronegative element. So there's no group 1A or 2A here, no fluorine, no hydrogen. So the most electronegative element is oxygen, and so it's going to get its preferred oxidation state. And so now, we have 3 of those. So we know that the sum of iodine plus the 3 oxygens is going to be -1, which means that the iodine has to be a +5. Here, let's give first hydrogen is +1, each oxygen is -2. That means that we have 1 plus the chlorine plus 3 oxygens is 0. So when we solve for chlorine here, we also get that this one is +5. Silver chloride, no group 1A or 2A, no fluorine or hydrogen. So chlorine gets its preferred oxidation number, -1. And so we know that then we have -1 plus the silver yields 0, which implies then that the silver is +1. And this last one, we do have a group 1A, and then we have oxygen. And so we have the potassium plus 4 oxygens plus the manganese is equal to -1. Rearranging and solving for that, we get that the manganese is equal to +6. Okay, that's it for this video. Thanks for watching. If you have any questions, you can ask in office hours, piazza, or recitation.